Welcome to The Explainer. Today, we are diving into a massive, and I mean massive shift in the world of artificial intelligence. We're officially moving past the era where AI was just, a neat supercalculator that spits out answers to basic prompts. It's actually evolving into a true collaborative partner in deep mathematical discovery. We're talking about AI systems teaming up with human researchers to uncover brand new, never-before-seen math.
So I want you to just consider this question right off the bat. What happens when an AI stops taking math tests and actually starts discovering new math? Because it's one thing for a machine to solve an equation where we humans already know the answer, right? But it's an entirely different ballgame when we venture together into the complete unknown. Today's Explainer investigates exactly that, looking at some groundbreaking new research that gives us a glimpse into the incredible future of human-AI collaboration. To really get how this works, we first need to define what we mean by agentic AI. Basically, this is an artificial intelligence system that autonomously orchestrates external tools, models, and solvers to achieve complex, open-ended goals. Think of it like a conductor leading a massive, complex symphony. Instead of just playing one single instrument, the AI is up there waving the baton, directing a computer algebra system over here, a formal proof checker over there, and ultimately orchestrating a beautifully verified mathematical result.
All right, let's dive right into part one. Meet the AI co-mathematician. Here is the actual technical engine driving this whole thing. We're looking at the Numinalian agent architecture. And right away, you have to understand, we aren't just dealing with a standard language model sitting in a chat window anymore. No way. This is a general coding agent. It's actually built on Claude Code, and it uses something called a model context protocol to directly access formal theorem provers like Lean. It isn't just taking wild guesses. It's actively writing code to formally verify its own mathematical logic step by step.
Let's break down this modular toolset a bit because it's super cool. The agent essentially relies on four main tools. First, you've got Lean LSP MCP, which is what interacts directly with that Lean theorem prover. Then there's LeanDex, which basically acts like a highly specialized search engine pulling up relevant theorems and background knowledge. Third is the informal prover, which drafts and refines proofs in plain English. And finally, my absolute favorite, the discussion partner. This tool actually queries other, entirely separate language models to get a second opinion when it gets stuck. Together, these create this incredibly robust trial, feedback, and optimization loop. If a proof fails, the agent figures out why, searches for a new theorem, talks it over with another model, and tries again.
Okay, moving on to section 2, acing the Putnam benchmark.
So before researchers let this thing loose to discover totally new math, they had to validate its baseline capabilities. And wow, did it deliver. 12 out of 12, a completely perfect score on the Putnam 2025 exam. If you're not familiar, the Putnam is this notoriously brutal mathematics competition that tests the absolute brightest undergraduate minds in the world. And the Numinalian agent? It solved every single problem. Absolute baseline competence verified.
Now, what's really fascinating about these numbers is the comparison. The Numinalian agent is an open-source system built on a general coding agent, right? Well, it perfectly matched the 12 out of 12 score of Axiom Prover, which is a highly specialized closed-source system. It even beat out Harmonic's Aristotle system, which scored a 10. This is a massive deal because it proves that an open agentic approach is currently operating at the absolute state-of-the-art level in complex mathematics.
Which brings us to section 3, exploring the unknown.
All right. Now we are shifting the narrative away from those benchmark tests where we already know the answers, and we're heading into the totally uncharted territory of open mathematical problems. To ground us real quick, we need to define what a Latin square is. It's essentially an n by n array filled with n different symbols, where each symbol occurs exactly once in each row and each column. Just think of a Sudoku grid, but a more generalized version. They are fundamental objects in combinatorics and actually have huge real-world applications in designing experiments.
So here's the open problem the researchers wanted to tackle. What is the minimum possible spatial imbalance for a Latin square when perfect balance is mathematically impossible? Or putting it simply, how evenly can we distribute these symbols when the underlying math absolutely refuses to divide cleanly? Well, when human researchers and computer solvers tried to find this minimum imbalance for certain notoriously difficult sizes, they smacked right into a combinatorial wall. The search space just grew super exponentially. Traditional exhaustive algebraic search completely failed. It was a total dead end.
Let's move to section 4, the human-AI pivot.
So how did they get out of that dead end? Let's walk through this incredibly suspenseful discovery journey, which played out across 5 distinct phases. Phase 1 was that dead end we just talked about, but phase 2?
That was the research pivot, where the human actually had to step in. Then in Phase 3, the parity anomaly. The AI spotted something wild in the data. Phase 4 brought in that parallel AI to check for errors. And finally, Phase 5 was the computational extension that found brand new, near-perfect permutations. Let's look a little closer at how this human-AI tag team actually worked.
The entire breakthrough really hinges on this specific quote. The critical decision was to change the question entirely. Instead of searching for objects with zero imbalance, we asked what is the minimum positive imbalance. I want to emphasize this because it highlights just how indispensable the human researcher still is. The AI agent, with all its massive computational power, didn't think to abandon the original search. It took human metacognition, human intuition, to look at that dead end, take a step back, and entirely reframe the objective.
But once the human moved the goalposts, the AI agent went to town on the numerical data. By inspecting just mountains of shift correlation data, which is basically how the positions of different symbols relate to each other, the AI noticed a hidden pattern. It saw that all the values were unexpectedly even. And from this, it formulated the crucial parity lemma. You know, this is a pattern a human mathematician would almost certainly miss in that endless sea of numbers, but the AI recognized it effortlessly. It figured out that because all the distances were even, the minimum deviation per pair had to double. And that single insight, it cracked the whole case wide open.
Now, the next part of this brilliantly illustrates the nuanced reality of working with multimodal AI right now. During the proof process, the system queried other frontier models to review its work, and the researchers found this fascinating asymmetry. On one hand, the AI was highly reliable for criticism. It was amazing at catching subtle logical errors and overgeneralizations in its own proof drafts. But on the other hand, it was surprisingly unreliable for constructive claims. It would sometimes just confidently state totally incorrect mathematical scaling claims that completely failed when put to the test. So it's a phenomenal critic, but you definitely still have to verify its creative leaps.
And that brings us to Section 5, the future of discovery.
We've seen the human pivot, the AI's insane pattern recognition, and the rigorous automated checking. So what was the actual real-world result of this partnership? Well, by combining neural pattern recognition, symbolic computation tools, and human strategic direction, the team successfully proved a tight lower bound on the imbalance of these Latin squares. And it's backed by newly discovered near-perfect permutations. Best of all, they formally verified the whole thing. This isn't just an estimation. It is a genuine, documented mathematical discovery produced by an agentic neurosymbolic system.
Which leaves us with a pretty provocative final question to ponder today. If an AI can uncover these hidden structures in vast oceans of data, while human intuition steers the ship out of dead ends, what impossible problem are they going to solve together next? We are truly standing at the edge of a completely new era of scientific discovery. Thanks so much for joining me for this explainer, and keep learning.